Hi everyone, my name is Stuart Thickett from the University of Tasmania, and today I want to tell you a little bit about some of the work we've done on the preparation of polymer-silica nanocomposites of various morphologies by a technique combining raft polymerization and subsequent sol gel chemistry. So we've been interested in colloidal nanocomposites for a really long time, and polymer-silica composites are arguably the most widely studied class, and there's lots of published methods in preparing such colloidal nanocomposites, primarily involving either the polymerization of a vinyl monomer with a silica precursor, such as a vinyl silane, or indeed the polymerization, such as an emulsion polymerization in the presence of silica nanoparticles. But as you can see from the images on the screen, they all yield spherical morphologies as a resultant particle structure. So the question we asked was, how can we access different morphologies for such composites? We were inspired by using the idea of block copolymer self-assembly, which has been well known for an extensive period of time to prepare self-assembled aggregates of a variety of structures, including spheres, rods, lamellae, vesicles, and so on, using block copolymers where one block is selective for the solvent and the other block being a non-solvent. These are typically produced by the solvent exchange method, and the morphology that's produced is typically dependent most prominently on the volume fraction of each block in the copolymer. The drawback of this technique, however, is that the approach is normally performed at high dilution, so scale-up presents a significant challenge. Polymerization-induced self-assembly, or PISA, however, has been the real revolution in this space to prepare composites or polymer nanoparticles of a variety of morphologies at high solids content. And the key point is that the system starts in a non-self-assembled state, using advances in techniques, primarily through raft or ATRP polymerization methods. We first grow a solvophilic block, which is soluble in the reaction medium, and then we undergo a chain extension process with a solvophobic monomer, leading to the onset of self-assembly, and then as we increase the length of the core forming block, we ultimately achieve higher order structures such as cylinders, worms, and ultimately vesicles. There is an emergence in recent times on the idea of surface-initiated PISA from silica nanoparticles, where typically a raft agent is grafted to the surface. But again, we're starting with a preformed nanoparticle and we're performing surface grafting from that. What we wanted to do that was a little bit different was to use PISA primarily as a structure directing motif to create colloidal nanocomposites, where our solvophilic block carries a reactive alkoxysilane group, such as shown here, commercially available alkoxysilane methacrylates, the trimethoxysilyl version being commercially available, and the triisopropoxy version readily made in the lab, using this as our solvophilic block to then ultimately perform chain extension with a solvophobic monomer, such as benzyl methacrylate in ethanol. All things going well, this alkoxysilane group is still active after the second step and can be used to grow a silica shell via subsequent hydrolysis and condensation of the tetraeth of a precursor such as TEOS, preserving either the spherical or vesicle or capsule-like morphology formed during the polymerization. So Chris, who recently graduated, started off by making a variety of macro raft agents using both the methyl and isopropyl versions of this alkoxysilane, targeting 40 or 65 repeat units respectively, with reasonable control of the molecular weight distribution. There's some slight variations between the methyl and the isopropyl version. It's important to point out that in solution, these polymers survive the polymerization process. The silicon NMR is very instructive in this sense. We get a single peak due to the trimethoxysilyl group in the case of MPS polymerization, indicating there's been no intra or intermolecular cross-linking during the polymerization process. When we perform our chain extension with typically 400 units of benzyl methacrylate, we see a nice clean shift in the case of our isopropyl stabilized system. The trimethoxy stabilized system gives a nice clean primary peak, but there is some higher order stuff, which is mainly attributed to, which we can attribute to chain cross-linking during storage. We have to obviously precipitate, isolate the polymer prior to SEC, which greatly enhances intra and intermolecular cross-linking, and we end up with a lot of insoluble substrate that we can't analyse. We can see here over on the right hand side of the figure that if we perform our chain extension in the presence of our MPS block, it is indeed acting as a stabiliser. We get a nice clean colloidal dispersion as a result. If we don't have our MPS block present, we end up with a precipitate, of course benzyl methacrylate, polybenzyl methacrylate not being soluble in the reaction medium. We then went on to look at how the length of the benzyl methacrylate block influences both the size and morphology of our resultant particles, and if the length of the benzyl methacrylate block was quite short, 100 units, we would of course form spheres, being the first self-assembled structure that does form. With our longer stabilising block, MPS 65, we exclusively form spheres across a wide range of DPs for the second block. We could of course tune the size of our spheres from approximately 100 to over 200 nanometers Z average diameter. But this is typical of long stabilising blocks that essentially prevent the fusion and rearrangement of our self-assembled structures. Dropping the length of our stabiliser block from 65 to 40 did indeed yield vesicles from approximately a DP of 150 onwards of the benzyl methacrylate block. And we can see by TEM the presence of quite clear demonstration of vesicles that collapsed on the electron microscope grid of relatively uniform size and thickness of the wall. Comparing our methoxy results to our isopropyl stabiliser, regardless of the length of our core forming block, we could only form spherical morphologies. And that's attributed to this greater steric bulk of our triisopropyl stabiliser compared to the trimethyl version. Across a very wide range, well over 1,000 units of benzyl methacrylate incorporated, we form essentially spherical nanoparticles. Again, we're inhibiting the rearrangement to form higher order structures in that case. Once we'd formed our nanoparticles, the next investigation that we performed was to then grow by controlled base catalyzed hydrolysis and condensation of our silica precursor onto the surface of our nanoparticles using a controlled feed method. And we can see here both by the DLS distributions as well as TEM and SEM that we form a uniform shell of silica, typically between 30 and 50 nanometers in thickness, on, in this case, our polymeric vesicles. If we quickly flip back to what our particles looked like prior to the growth of the silica shell, we can see that the vesicles have collapsed under the high vacuum conditions of the electron microscope. Compare that to when the silica shells are present, we have a greater retention of structural integrity due to the highly cross-linked nature of our now silica shell on the surface. When we used the isopropyl surface, the isopropyl functional nanoparticles, we do get a controlled growth, but our morphologies are no longer smooth. They are essentially lumpy or raspberry in nature, and that was attributed to the difference in the hydrolysis and condensation rates of the methyl group, the isopropyl groups on the surface, and the TIOS precursor. We also wanted to try the idea of switching things around and using MPS as a core forming block in a raft emulsion polymerization system. This, however, was unsuccessful in that sense. We were not able to use this monomer easily under aqueous conditions due to significant condensation of the monomer at the reaction temperature, as emphasised by silicon NMR studies. And so we had to return to a solvent-driven self-assembly method, preparing our block copolymers with a PEG stabilising group with an MPS as the core forming block, and adding water, non-solvent for the MPS block, to a solution of the polymer in dioxane. Again, this only yielded spherical nanoparticles, which was attributed to MPS cross-linking upon self-assembly. And we could demonstrate this by trying to redissolve or disperse our polymers back into their unimer state, which was not successful, even in the absence of any base to cross-link the material. We also wanted to investigate, can we form capsules by an interfacial cross-linking and stabilisation method. The approach that we used was to use triblock copolymers with a PEG methacrylate block as the corona, the MPS block in the as the interfacial region, and benzyl methacrylate as the core forming block. Use these tri-blocks to stabilise oil in water emulsion droplets, and then cross-link that interface through the addition of a water-soluble base. We could indeed demonstrate that principle. What we were able to observe was that prior to the addition of the base, obviously we had the emulsion droplets approximately a micron in size, form, cross-linking the solid lines, prior to cross-linking being the dashed lines. If we add that system back to a good solvent, namely dioxane, we would see dissociation to the unimer state, but that was of course not what we observed in the case of post cross-linking, so we were able to preserve that capsule morphology in an organic solvent. A secondary approach to attempt to do this was to use, again, the PISA method to polymerize or form triblock copolymer nanoparticles, again with an MPS functional interface. And again, before and after cross-linking, what we were able to see was good correlation before and after the cross-linking process of the particle size distributions in both water and dioxane, with a dissociation back to the unimer state prior to the cross-linking procedure taking place. What you'll notice is that we didn't actually form, even for very asymmetric block copolymers, anything other than spherical nanoparticles, again attributed to the fact that this long stabilizer block with the MPS group at the surface, essentially restricting the rearrangement to form higher order structures. So to conclude, I hope I've demonstrated that we can prepare colloidal nanocomposites using a combination of polymerization, induced self-assembly, and sol gel chemistry, where spheres, vesicles, and capsules were prepared in a controlled fashion with good control particle size. And by then using that as a resulting polymer nanostructure, we can then functionalize the surface with other alkoxysilanes. I want to acknowledge the students, in particular Chris Teo, who did the work. I'd like to thank UNSW for their help with electron microscopy analysis, University of Tasmania, and of course you for your attention. Thanks very much.